6.5 is going to continue on with integration, and we're going to be doing both integration of indefinite and definite integrals. However, what's going to be happening with 6.5 is a build on into the rules that we have already. So we have 5 basic integration rules. For example, how do you integrate a constant? So we have these basic rules that are out for us. Now we're going to have some sort of function that does not fit these 5 basic integration rules. So we're going to learn how to recognize this and then use what we call the use substitution process to integrate this in a different manner. Alright, I want to bring us back to old ways of differentiating, so when we were deriving. So let's look at something like this. If I were to want to derive this function right here, so I wanted to find dy with respect to x, there's these rules that we always have to follow. There was nothing that ever stated that, okay, so I have these 2 different kind of pieces being multiplied. I have 2 factors being multiplied. Why don't I just derive this times the derivative of this piece? There was no rule that said that. So the idea is we had this rule called the product rule that stated you can derive this, but what you're going to have to do is take the derivative of the first, so d times your second. So times, and I would just write x plus 1. This is how we kind of got in the habit of doing it. Plus, now you're going to leave your first one alone times the derivative of your second. So that was our product rule that we could follow by. Same thing here, we had the quotient rule, the low to high minus high to low all over low squared. And then something like this where we had a function within a function. It's not that you could ignore the fact that there's this extra exponent here and just derive what was on the inside and throw that extra exponent on the outside. We couldn't do that. We had to use that chain rule of, and we're going to head into the chain rule a lot today, but we would have to leave the inner alone, derive the outer, but then multiply the derivative of the inner. So now when we're getting into integration, please don't just make up some sort of rule. We've had the 5 basic rules of integration that we've been going by, and I'm going to have a flashcard of that up here to remind you of those. But please just don't make anything up and say, oh, I don't really know what to do with this exponent, so I'm just going to integrate this inner piece and leave this exponent alone and tag that on back later. Don't just make things up like that, because we have these rules and processes that we have to go by. So once again, here are on page 390 some of the basic integration rules. So if you ever are integrating the number 0, you're going to get a constant. So there are those 5 basic ones. What we've been practicing with so far is something like this could use any one of these properties up here that apply. Alright, but if you now look at something like this, what do we do with a function within a function? This is a composition function right here. I have this function that's all brought up to the 1/2, so it's a composition function. There's nothing that we have so far that addresses this. So right now, you cannot do that, but we will be able to. So we're going to review now the chain rule. So to get into how we integrate a composition function, let's go back to how we derived a composition function. So consider this one right here. Okay, and what we did in the past with the chain rule, I'm going to draw this step by step. I'm going to do it the quick flash way, but then we're going to break it down into how we got to this point. As we've been practicing, what eventually we got to the point was, well, leave this inner function alone, but let's drive this outer. So I'm going to pull down this 1/2, leave that inner function alone, and then reduce this by 1. So I have 1/2 minus 1, which would have been negative 1/2. Okay, and then times, though, this was important, you have to multiply this outer function that's been derived with the inner function left entirely alone, and now you have to actually derive that inner function. So what's the derivative of this inner function? Well, bring down that 2, we get 2x to the first. I'm going to leave that minus and then 0 because it's just a constant, so that would drop off as we derive it. So this right here, in the end, what we're going to get is those would cancel each other out, the 2 and the 2. My final answer would. So let's do a breakdown of what this was. How did we go about doing this? Well, when we had a composition function, say f was a composition function, what you would have to do is identify an inner function, leave it alone at first. And then what we would have is, alright, f prime of u, so we would actually derive the outer function that I would call f, by leaving that u alone and multiply it by the inner function's derivative, what we would call dy du, or I'm sorry, du dx. U was equal to that inner function x squared minus 1. Alright, and so then du dx, let's derive u with respect to x, du dx. And if I wanted to write this as a differential, I could. I could relate the change in u with the change in x by writing it as a differential. That's one of our vocab words. And I could just multiply dx to both sides. So du equals 2x dx. We're going to look at y then. Y would be equal, we're going to look at the equation now with respect to u. So let's pretend we took this out, this inner function out, and just rewrote u. So y is just, but otherwise you can also rewrite this as f of u is equal to u to the 1/2. Okay, so if we took this out and started to write it with respect to that inner function, we would just get f of u is equal to u to the 1/2. So therefore, y prime, and then otherwise we could look at f prime of u, that would be equal to 1/2. I mean, same thing, it's just two different notations. So finally, what we're saying is, for what the chain rule says, what the chain rule says is if you derive a function f, and where f is going to be some sort of composition function, a function within a function, then go ahead and derive the outer, leaving the u alone, the inner alone, but then go back and multiply by the inner's derivative. So this is what we had right here. This is our f prime of u. F prime of u was equal to 1/2 u, 1/2 u, which was our inner function, to the negative 1/2 times, and then we had to multiply this whole thing by du. So here was du, here was f prime of u. So this is what we're going to do now. This is also notated as dy with respect to x. The derivative of y with respect to x was x times. Okay. So here, if I were to rewrite this as a differential, so an equation that relates the change in y with the change of x, we could rewrite it as this. Okay, multiply that dx to both sides. And now if I were trying to say, alright, this was my differential, and I want to work backwards, it's something, clearly, you can see that dx, it's clearly something that's been derived. So let's work backwards, and let's find out what that original, that big F, what we would now notate as big F of x, what is the equation that we derived to get this. So I'm going to integrate both sides. So now what we're looking at is f of x, big F of x, is going to be equal to x times x squared minus 1 to the negative 1/2 dx. Whoops. And this is what we're going to work on getting, or work on solving. So there's a certain pattern that we're going to have to recognize, and we're going to pull that up in the next slide. But hopefully what we're going to be getting back to is this. Alright, so here is the slide that I would like you to look at. If you ever see a pattern that looks like this, we have an inner function, a composition of some sort of inner function, and then we have the derivative of that inner function being multiplied. Looking back, what we have here is the composition. This was some sort of composition. This is some sort of f of u. Okay, and then what we have is the derivative of u on the outside, and you'll kind of see that. So a du that's also being multiplied. So a composition function, an f of u times, and then the inner function derived being multiplied. That's when we can go ahead and rewrite it as this. And we'll do examples of this in a second. Otherwise, this is just a different notation that means these mean the exact same thing. This right here means the exact same thing as this right here. But instead we're just saying, alright, g of x would be what identifies the inner function versus u. And then the general power rule, this should actually have a du here. So if you ever have u to the n with respect to u and you're integrating it, then it's the same general power rule that we used before. Then just add 1 to that exponent, and then you would divide by that whole entire new exponent. So this is nothing new. Same thing, except we're just letting g of x symbolize u, so some sort of inner function to some sort of power. What you can do is take that inner function, add 1 to that exponent, and then divide by that new exponent. There are guidelines for integration by substitution on page 437. I'm not going to go through those at this moment. I would ask that you look over those guidelines. What I'm just going to do is show you that process, and hopefully by example you'll begin to understand. We're going to do example number 1. And what it says is identify the u and the du for the integral. So what we're trying to identify is u, or in other words, if you want to, you can also say that that's the same thing as gx. Basically, we want to identify the inner function. Okay, and then we also want to identify what would be then the derivative of u. So in other words, g prime of x dx, if you also want to look at it that way. So what I'm going to say is, normally if ever you see something brought up to a power of some sort, that's normally going to be that composition function that you're looking for. And so right here, I'm going to identify u as that inner function that's being brought up to the second power. So in this integral, what I'm going to identify is this right here was my composition function's inner function. Okay, and then so therefore du would be equal to, or du dx would be equal to, and then I would bring down that 2, I would get 10x and then plus 0, so in other words, there's my derivative. You're done with it. That's all it required you to do. I do want to just go into now the process of u substitution. It's important that we're able to identify the inner function and then go forth and derive it. For this reason. So again, you don't have to do this, but I just want to show you this process. The steps for this process are on page 437, but I think it will be most helpful to see it by example. Now that we've identified this inner function and then also the derivative, I am going to rewrite the derivative as a differential equation. So I'm just going to multiply that dx to both sides. What we get is 10x dx. What's going to happen here is, in this process of trying to integrate these composition functions, you're going to try to remove all of the x's and replace them with u's. And that's why we had to do this. We just wrote two equations that linked u and x together. So what you're hoping is you can put u in and then take out these x relations. This 5x squared plus 1, this 5x squared plus 1 is going to be replaced by u. We're going to substitute, since they are equal, we are going to substitute u in. So it's going to be u squared. And then the other thing that I have here is a 10x dx. So here's that 10x dx. I'm going to replace that with what it is equal to, that relationship that we found, and it is equal to du. Alright, so now here is where that general power rule comes into play. We're trying to integrate something with respect to u, and it's just a singular u variable to an exponent now. So what I can do is, we're going to get u to the third, divided all by 3, and then because this is an indefinite integral without any bounds, we're going to have a plus c. So now, not quite done yet, this would be 1/3, and then I'm going to go ahead and replace now my u back with the x. So what u was equal to was 5x squared plus 1. This is all to the third, and then a plus a constant. Alright, so what we did was we labeled these big F of x's. This is the differential that we were given. Alright, and it was a clearly labeled derived equation, and what we wanted to do was figure out what was the equation that was derived to get it. This is it right here. If I wanted to check this is how I would go about doing that. I have found that f of x is equal to this whole thing. What's going to happen now is I want to check to make sure this works. Is this the antiderivative of this? When I derive this, do I get this? So here I go. This would require the chain rule because I have a composition function. I'm going to have to bring down that 3, leave the inner one alone, reduce the exponent, and then multiply by the inner function derivative. So I'm going to get 3 times, reduce that outer degree by 2, and then I have to go in and multiply the inner function's derivative. So okay, and then I get a plus nothing. Because it's a constant. So those cancel each other out. What I do get, yes, when I derive this antiderivative equation, this general antiderivative equation that I found, when I derive it, I do in fact get this, the 5x squared plus 1 squared 10x. Okay, more examples are to come in the next video on this process of u substitution.